All right. I remember when I was in third grade. It's one of the you guys like in your life you have like these crystallizing moments, right? When teachers really like click and connect, or something a teacher says really clicks and connects with you, right? I remember in third grade, and I will never forget this, when a teacher in a science class was like said something to us, and they're like, "Cold doesn't exist. Cold is not a thing." Okay. There is only more or less heat. Okay, so you feel something that's cold, right? And we go, that's cold. Cold exists, right? There is no such thing as cold. There is just more or less heat, okay? Because we need to learn what heat actually is, okay? So cold's not a thing that exists. Things can be less warm than you, and you can feel them as cold. So we do like experience cold. Cold is a useful idea, but it's not a real thing, right? It's just more or less heat. So we have to understand what heat is, and how that pertains to matter. Okay, so let's start off here. You know, probably, that matter has three traditional states that it can be in. Okay, matter can either be a solid, a liquid, or a gas. And you know that matter can, hopefully you know, that matter can change from one state into another. Okay? Um, what's probably the best example? What kind of matter is probably the best example to talk about all three? Water. Water is the best example to talk about all three. Okay? Um, so let's talk about solids first. Okay? What's the solid form of water? An ice cube, right? So ice. So you take ice cubes and you put them into a glass, right? Do those ice cubes, assuming they don't melt, so ignore melting right now because that's liquid, right? So assuming they're a solid, do they change their shape? No, they just kind of stack up on each other, right? They don't necessarily fit together in any important way. Do they occupy more or less space? Do they change the amount of space that they occupy at any given time? Like an ice cube here, if it stays an ice cube, are you going to be able to squeeze it into a space smaller than the ice cube? No, right? If I have a 10 centimeter by 10 centimeter ice, if I have a big ice cube, 10 centimeters by 10 centimeters by 10 centimeters, and I try to put it into a 5 by 5 by 5 box, I just can't fit, right? The ice cube has a definite shape and a definite volume. It occupies a definite amount of space that doesn't change, okay, and it has a definite shape to it, okay. Now you can shape the ice cube, right, by melting it, okay, but in its solid form, or breaking it, right, breaking the chemical bond, but in its solid form, ice has a definite shape and definite volume. Well, what's happening here is when an ice cube goes from liquid to ice, what is water? Yeah, but what is it though? What's it made of? H2O, right? Hydrogen, two of them, and one oxygen atom. Okay, that has a structure, right? It looks like Mickey Mouse's ears. So two hydrogen atoms, one oxygen atom. It has a shape to it, right? Well, atoms vibrate. They have what's called kinetic energy. The electrons orbiting atoms have kinetic energy, okay? And this causes the atoms to jiggle and vibrate, and they bump into each other, okay? When there is enough kinetic energy in the material, water in this case, in the matter, the atoms will bump into each other and then just brush by each other. Okay, they won't stay next to each other. The atoms will shift around and move around past each other, slip past each other. That's a liquid. Okay, if you take and remove some of the kinetic energy from those molecules of water, those molecules of water will slow down, okay, and begin to link up with each other and bond together in a certain way, making a solid. Okay, so the difference between a liquid and a solid, or a gas and a liquid, is the kinetic energy of the molecules. In fact, that's what temperature is. You say it's 71 degrees in this room. You're telling me the average kinetic energy of the molecules of air in this room. Okay? And as the temperature goes up, it gets hotter. Those molecules move faster and faster and faster, and they bump into things faster and faster and faster, more kinetic energy, and you feel that as more heat. Okay? Objects change from gases to liquids to solids when their kinetic energy of their molecules reaches these threshold points, okay? When does water move from a liquid into a solid state? So you guys know the temperature, right? You just said it. 32 degrees Fahrenheit, right? Or 0 degrees Celsius or centigrade, okay? So let's use Fahrenheit because everyone's used to that one, right? If you have your freezer set at higher than 32 degrees Fahrenheit, the temperature of your freezer, the average kinetic energy of the molecules in the freezer will be so high that the objects cannot solidify. They can't turn into solids, okay? But if you lower the temperature in your freezer below 32 degrees Fahrenheit, the kinetic energy of the molecules of the food that you're storing in your freezer they'll all crystallize. They'll turn from a liquid, it's the water in your food, turns from a liquid into a solid. Below 32 degrees Fahrenheit, water turns from a liquid where the molecules can all slip past each other into a solid where they're sort of locked together and have a definite shape and definite volume. You take the ice cubes out of your freezer and you put them on your counter. And in your room, your ambient temperature is something like 71 degrees, which is usually room temperature on average. And what will your ice cubes do? What do your ice cubes do if you set them on the counter? They'll melt, right? What is melting? It's a change of state, right? They were a solid, and then they're turning into a liquid, right? Once the ambient temperature around the ice cube is higher than 32 degrees Fahrenheit, the air in the room, the molecules of the air in the room are going to begin to bump into the ice cube. And notice the ice cube doesn't melt from the inside, it melts from the outside, right? Because deep down on the inside of the ice cube, in the center, those molecules are all very, very slowly moving in there, right? The air in the room can't interact with the center of the ice cube. The air in the room has to interact with the outer layers of the ice cube first. So the air in the room begins to bump into the ice cube because the air molecules are faster moving than the ice cube. The air in the room deposits kinetic energy into the ice cube. It is true that when right around the ice cube, the air in the room will be colder than the air further out in the room. Because the air in the room that's bumping into the ice cube is giving kinetic energy to those ice cube molecules, those water molecules, and that air is losing energy. The air is actually getting colder. If you put your hand near an ice cube, the air is colder near an ice cube because the air in the room is depositing kinetic energy into the ice cube, increasing the molecular energy of the molecules of ice, turning the ice cube from ice cube into liquid water. Okay. If you take liquid water and you put it on a stove over a source of heat, okay, again, heat is just energy, right? And you turn the stove on and you have that fire heat up your pot, right? The metal in the pot will conduct heat through it and so the metal's molecules begin to start to shake around more, okay, when you turn that fire on underneath. And the metal molecules shaking around, they give kinetic energy to the water molecules in the pot, okay? And the water molecules all begin to move faster and faster and faster and faster. Eventually, if left long enough, and if you watch it, it never boils, right? But if you walk away and let it do its thing for long enough, those water molecules will begin to not just slip past each other, like what happens in water, but move so fast that they separate completely, that they're not even touching each other anymore, okay? We call that a gas. Or when water does it, we call it what? Huh? Vapor. Vapor or steam, right? By the way, at what temperature does that happen? You guys know when water boils? 212 degrees Fahrenheit, okay? You want to know what's easier than that? Learning the metric system, okay? Because in Celsius, water freezes at 0 and boils at 100, okay? So much easier, right? You want to know what's happening with water? Well, 0 degrees it freezes, 100 degrees it boils, okay? Water doesn't boil and turn into steam at 99 degrees Fahrenheit, or 99 degrees Celsius, or 211 degrees Fahrenheit. It turns from liquid into gas at exactly 212 degrees Fahrenheit, and no more, no less. Okay? Fahrenheit's American. Yeah, it's British, but we've adopted it over here in the U.S. and we've kind of kept it. Yeah, even in Europe where this came from, they've moved to the metric system. Metric system was invented in France in like the 1700s. We took the standard units of measure, used them over here from the UK, and then the UK went ahead and moved to the metric system, and we kept the standard units. So the point here is, though, temperature is just a measure of the kinetic energy of the molecules in some matter. Molecules either vibrate faster with more kinetic energy, or they vibrate slower with less kinetic energy. If something is felt by you to be hot, that just means its molecules are moving faster than yours, and they're depositing heat into you, okay? If I touch my warm cup of coffee, I feel warm, right? And my cup of coffee has actually cooled down a little bit because of that. Some of the kinetic energy of the molecules in the coffee have conducted their energy into my hand because I touched it, and now the coffee's cooler because of that, okay? So what matters here is the kinetic energy of molecules increasing or decreasing. Now, the warm cup of coffee puts a little bit of kinetic energy into my molecules and I feel warm, right? But if I touch my oven door, the glass door of my oven, right? Assuming it's not a new oven, which does a pretty good job of insulating, but an old oven, I touch the glass oven door, what's going to happen to my hand? Oven's on, right? It's going to burn the crap out of my hand, right? I touch the oven door for 1 second, I might get a burn, maybe some second-degree burn, blisters on the hand. If I touch my coffee cup for 1 second, I don't get second-degree burns, right? Why do I get burnt when I touch the oven door and not when I touch my cup of coffee?
Insulation from the coffee.
Yeah, but let's say the coffee's not as hot, right? The oven's hotter. You set your oven to 400 degrees or whatever, right? 350, 400. You set your cup of coffee to a little over 100, more than 100, right? You don't set it to anything, but importantly, you warm your cup of coffee up, and it's not at 400 degrees Fahrenheit, right? It's 100 and something, 160, whatever. The cup of coffee has less kinetic energy to deposit into me, so I don't feel it as hot as I do when I touch my oven door, okay? And it's all due to the kinetic energy of the molecules. You know, when I put my hand down on the table, right? You guys put your elbows on the table, right? And you pick your elbows up off the table. Well, you're warmer than the table, and so you've put some energy into the table. You can feel the table's warmer now, right? You have lost some kinetic energy. Remember, conservation of energy, your energy doesn't go away, right? It just went into the table. Okay, you've conducted heat into the table, and now you have less heat. Okay, you're always conducting heat into your surroundings. That's the way heat works. Heat will never spontaneously flow from cold to hot. Okay, a cold object never heats up a warmer object. It is always the case that a warmer object deposits heat into the cooler object. Okay, because of this idea of heat flowing, before we knew about the atomic theory of matter that we know now, they actually used to think heat was a thing. Like heat would flow from my coffee cup into my hand, okay, or as I drink the coffee, heat would flow into my body with the warm coffee, right? They actually had a name for it. They used to call heat caloric, okay, which is where we get the name calorie from. Calorie in food, heat energy from food. So we used to call heat caloric because we thought heat was a thing, a fluid. It's not. Heat is just the kinetic energy of molecules, and everything's made of molecules. There is an idea called absolute zero, okay? So like there's 0 degrees Fahrenheit when like water freezes, right? But what if you could get colder and colder and colder? Eventually, because heat is just the energy movement of the molecules, right? Eventually, if you could cool something down enough, there would be no movement of the molecules. And we call that idea absolute zero. It's never been achieved. We've gotten within like billionths of a degree of absolute zero. And what's really cool, I encourage you, because I won't spend time on it today, I encourage you to go look up absolute zero and superconductivity, because what's really neat is when you cool something down to these extreme levels, there is no friction between the molecules moving. They don't lose energy. You can put in a container a super cooled form of matter, and it's not a solid anymore. It actually can flow up against gravity because it has no loss of kinetic energy from the molecules rubbing together. When you cool things down that much, weird things happen. Okay, it's called superconductivity or superfluidity at these close to absolute zero. But that's the idea: is that molecules move. They always move. We can, by using fancy equipment and engineering, we can slow molecules down to really slow speeds, close to absolute zero. But absolute zero is this idea where you can't get to it. Even outer space, even the vacuum of space is hotter than absolute zero. It is something like 2 degrees Kelvin. Kelvin is the system of measure unit of measure like Fahrenheit, but it's used to measure absolute zero. In any case, that's what heat is. Heat is just the movement of molecules in matter. Okay, so the sun sending you light and you feeling warm. Okay, the sun is not sending you anything that's actually warm. The sun is not hot when it hits your skin. Your skin gets hot. When you feel the heat, it's not the sun that's hot, it's your skin that's warming up. Okay? The sun's rays are depositing into you, your skin, your electrons are raising up from their original shell levels and jumping back down, releasing infrared energy that you feel as heat. You have a way to detect and feel heat, but it's not a thing. Remember, heat's not a thing. Okay, heat's not coming from the sun. Heat's not coming from you and me. Heat is something that we can measure, but it's not a thing that is independently exists. Okay, good. What else do we need to know about these states of matter? Well, we need to know something called Pascal's law as it pertains to liquids. Okay, Pascal says in an enclosed system, liquid system, any pressure applied to the liquid will be transmitted undiminished throughout the system. Remember from this previous slide, I'll go back in a second. Liquids have an indefinite shape, so I can pour liquid into any bottle that I want, right? But if I have this bottle filled with 1,000 milliliters of water, and I try to pour it into a container that only holds 900 milliliters, well, it's not going to fit because water has a definite volume. Okay, I can pour this into any shape container I want, as long as the container has the same volume. Water does not change in liquid does not change in volume, but can change in shape. So if you try to push on this column of water, the force I apply here is immediately transmitted undiminished through the column of water down to wherever the water exits. This is the entire principle behind the heart's contractions. Okay, the heart can pump blood because the heart is full of blood, and when it contracts and you push on the blood doesn't compress. The blood water has a definite volume, and so the blood just moves, is pushed along the system. This is how we can create our heart can create blood pressure. This is also why if someone has a bolus of gas injected into their veins and it makes its way to the heart will compress that gas because gas can compress. Gas doesn't have a definite volume, and no blood will pump, and the person will lose consciousness and die. Okay, this is why it's bad for like air to get into an IV line. Okay, liquid. Do you have a question?
Yeah, well, I mean, with that example of putting pressure on top of the water coming back down to the bottom, what if a person was in the water? What would happen because of that pressure? If the pressure is coming out from the bottom or has to try to exit somewhere because there's pressure being put on it,
yeah.
What would happen to the body?
So, hydrodynamically, the pressure for that person will be higher at the bottom of the container. So they'll feel more pressure based on the volume of water that's on top of them, not necessarily the pressure that's applied to the water.
Okay, so then if they were closer to the top where the pressure is being applied, it's
transmitted
as much as the bottom.
Exactly.
Okay.
That's why you get smushed when you go to the bottom of the ocean and not when you're at the surface.
That's why if you go down scuba diving and you come back up
Yeah.
really quick, you get the bends.
Yeah, there's nitrogen bubbles in the bloodstream, right? Because you're breathing compressed gas, right? And that gas is compressed in an air tank, and then so when you come up, that gas wants to expand. That creates these boluses of gas in your blood vessel, and they call it the bends. And you got to go into like hyperbaric chambers, and it's a whole big problem. And then you can't dive ever again. Yeah. Yep. So that's the thing about water. let's get a couple of change of state terms on the board, okay? I think we know a few of these. Melting is turning from a solid to a liquid. We've got that one, easy peasy. You know freezing, that's liquid to solid, losing kinetic energy. Condensation, right? If I take this out of the refrigerator, my bottle of water is very cold, right? Low kinetic energy. The air in the room around this bottle will begin to slow down, and water molecules in the air will begin to gather on the surface of this container because the air, kinetic energy in the air is slowing down, and we're going to get gas in the air turning into liquid on the surface of this bottle. That's why our bottles get sweaty when we take them out of the refrigerator. Unless, for example, they're the nice ones like you guys have, like those Yeti insulated, vacuum insulated bottles, which, you know, all the cold that's happening is insulated from the outside world, right? And, you know, your guys' insulated bottles are going to stay cold way longer than mine, because mine interacts a lot more with the room. By the way, the vacuum insulation in these bottles, you guys know how it works? It says it in the name, vacuum insulation. So in your bottles, right, your vacuum insulated bottles, there's an outer shell like that, and then there is an inner shell that you actually fill with liquid. Okay, so all this is filled with liquid, okay? And between the outer shell, which touches the air in the room, so air's out here, and the inner shell where the water is, all of this space is empty. They've evacuated that space. There's a vacuum in that space. So when your cold water interacts with the inside wall and cools down the inside wall has no connection except for at the very top where like the metal comes together, right? Has no connection with this outside wall because between the inside and outside wall, there are no molecules to shake, to vibrate. So this inside wall can get as cold as it wants, and the outside wall will never get cold, will at a much lower rate get cold, okay? Said in another way, the air in the room is warm, right? So the air in the room is gonna heat up this outside wall, but that heat has a very hard time making it to the inside wall, because in order for the heat to move, heat moves by one of three methods: convection, conduction, and radiation. Well, there is nothing to conduct, because conduction has to touch, okay? There is no touching, there's no molecules between that inside and outside wall, so conduction's out the window. Convection, you need liquid. There's no liquid in here, okay? Liquid or gas. But radiation, this inside wall will heat up and it'll radiate thermal energy into the inside wall, and so eventually your water bottles get warm, you know, but you know, how long can you keep your water cold in there? Like, will it keep ice cubes for a whole day?
Yeah.
Yeah, so you fill it up with ice and water, a whole day, right? Give me like an hour with ice and water in this, and it's not ice cubes and water anymore, it's just cold water, right? And so that's the magic of that vacuum insulation technique. It takes advantage of this whole idea that we're talking about heat is related to, or it just is the kinetic energy of molecules. Yeah.
So sometimes like I put ice cubes in here.
Yeah.
And then see I finish my water, don't fill it up. That ice cube turns into like a hole.
Yeah.
How does that?
Yeah. Okay. So the outside of the ice cubes are melting, right? Because they're touching the inside wall, right? But the inside of the middle of the ice cubes are not melting, so they the outside melts and the insides don't. They sort of fuse together. Okay. The outside melts, touches more ice cube because they kind of move together as the ice cubes melt, and then the cold from the inside of the ice cubes will collect everything together and cause everything to sort of freeze together. Yeah, yeah. You will find though that once that happens, there will be some pooled water in the bottom. Like some of the ice cubes will have turned to water, and that's part of the melting process. But yeah, so that's your evacuated bottles, right? Some companies do it better than others, right? That's why those companies are well known. Yeti, what's the other one? Hydro Flask is the other one. There's a couple good brands, and they do it well, right? Yeah, so that's vacuum insulation. One of the best ways of insulating stuff. By the way, if you want your vacuum insulated bottles to work better, you ditch those sippy cup tops. Okay, do you have more than one top for yours?
Yeah.
Do you have the one that just screws on like this?
Yeah.
Do you notice that those insulated tops are thick?
Yes.
Yeah, and that's not. It's basically just a thin layer of plastic with a straw. If you could do the experiment if you wanted, you could put cold water and ice cubes in that, see how long it takes for the water to turn into just cool water, no ice cubes anymore. count that time, and then do the next day, do an experiment with the top, right? Leave it on, and see how long that takes. It will keep the water cooler for longer because that top is insulative as well, and that top is not. But no, they're great either way, though, right? But you can do those experiments to show that. Yeah.
We
Yeah.
have two of those too, like that, one that has one like that, and the one that he's talking about, and that one that you're talking
Yep.
about will keep ice in for
A lot
24
longer.
hours.
Yeah, a lot longer. Yep. I learned that pretty early on, and
I was wondering why.
yeah.
My cheaper is fake.
Just the top. Yeah. Because I mean, the walls in the bottom, because the walls in the bottom are insulated, right? But the top is the only spot that's not insulated, and
Why
yeah.
is it because like there's a hole?
There's just there's no insulation between the atmosphere, right? The only thing separating the atmosphere in the room from the water in the bottle at the top of the container is a layer of plastic, a thin layer of plastic. When you get the other lids, they have a thick layer of plastic and foam, right? That's what's in there is foam, and those thick lids, and so that foam adds insulation.
It's
And
like had rubber or something too.
Yeah, it's like I don't know. It's on the outside.
yeah.
That makes sense.
Yep.
No, I thought I got a cheap.
No, it's just different, better insulation. Yep. You would find that if you did that experiment with both of those, better yet, take two of them, right? And one exactly the same, one with the sippy top, and one. Yep. There you go. You can show it. All right. Good. All right. Last on here, evaporation, liquid to gas. Good. Now, there is another class of materials called resins. Resins, a good example of resins are most rubbers are resins, okay? Resins don't change state. Like water goes from, it is either a solid, a liquid, or a gas. There's no like in between for water. There's no like water doesn't get a little bit watery. It's either water or solid, right? Resins do not go through thresholds. They don't have, you would say that the water had a phase transition. When water goes from solid to liquid, it's called a phase transition, okay? That happens at a specific temperature. Remember, water goes from solid to liquid at 32 degrees Fahrenheit, okay? And goes from liquid to gas at 212 degrees Fahrenheit. Well, resins, they just gradually change as you increase their temperature. They go from being solid to being kind of bendy, to being a little bit more bendy, to being kind of liquidy, and they kind of just, there's no phase transition. They just sort of change state as it goes, okay? This allows resins to be reshaped by heating them and then letting them cool. That's why we can build things out of rubber and plastics. Plastics are another good example of resins. All right, and yep, the concept of cold is really just less heat. And again, I will never forget that from being in literally third grade and on. I will never forget that. And then I learned it again, when I learned this stuff as a student, and I went, oh yeah, that makes sense, right? Because it's just less kinetic energy. Energy doesn't disappear. When a substance is cooled, its kinetic energy had to be converted into something else. Okay. Do we give the refrigerator? Yeah, we do. So a refrigerator, right? You put a warm thing, like you usually let your dinner cool down before you put it in the fridge. But let's say you put your warm dinner in the fridge. Put it in a Tupperware container, put it in the fridge, and take it out an hour later. It's cool now, right? Where did the heat go? Right? Well, the heat went out the back of the refrigerator. Okay. The refrigerator works by pumping gas through a compressor, compressing gas, moving it through the refrigerator and expanding that coolant around the walls of the refrigerator. And that coolant sucks up the heat. That cold coolant sucks up the heat being radiated by the food inside of the refrigerator, removing the heat from the food in the refrigerator, cooling your food. Well, that heat goes somewhere. The gas that you're running out through the walls of the refrigerator warms up. So it goes to the back of the refrigerator. The coolant is put through a compressor. The compressor compresses the gas again, makes it hot, and you'll notice that if you put your hand at the back of the refrigerator, your back of your refrigerator is very warm, okay? By the way, that's the only thing that ever goes wrong with refrigerators is the stupid compressor, right? The compressors go bad because it's the thing doing the work for the refrigerator. It's the thing pulling the heat out of the inside of the refrigerator and shoving it out the back, okay? When ice cools a drink, the drink is heating the ice, not the other way around, okay? Remember, cold doesn't flow to hot. Hot flows to cold. The water in your beverage is heating up the ice cubes and changing the ice cubes from a solid to a liquid, okay? And eventually it goes from glass of water with ice cubes to just cool water, right? Because the water gave heat to the ice cubes, so the water cools down and the ice cubes warm up, okay? So what's heat then? Heat is just the flow of energy from one molecule to another. That's all heat is, okay? Internal energy has two components: kinetic energy in the form of temperature, movement of molecules, and potential energy as in the state of the molecules. When a substance is heated, the flow of energy into it may cause it to either increase its temperature or raise up to a higher position, such as when water turns to steam. So that's heat. That's what heat is. And as I mentioned with the water bottle analogy, and I'll mention it again explicitly, there are three ways that heat is transferred between molecules. Okay? Heat is either conducted by direct contact. I'm holding my pen, and if I gave you this pen after me holding it, you'd go, yeah, that pen's a little warmer than last time I saw it. Okay? I'm conducting heat into this pen. Convection requires fluid or gas. Okay? If we're in a cold bathtub, okay, I don't know why we're all in a cold bathtub, but we're in a cold bathtub, okay? So somebody dumps a warm bucket of water in the bathtub, that warm water will mix with the cool water, heating up the cold water in the bathtub, and the water that we dumped in will cool down. That's convection. The ocean deals with convection currents all the time. It's what drives this sort of worldwide weather patterns that we have, right? When a cold system, a literal cold system of gas mixes with a hot system of gas, you get the gas air in the atmosphere shifting around in its position. That's convection, changing the position and state of the molecules in let's say, the atmosphere. It's why we get weather, or one reason why we get weather. Lastly, and important for our purposes, radiation, okay? When you put energy into a molecule, the molecule vibrates more. Molecular vibrations emit electromagnetic waves. When a molecule vibrates more often, it will emit more electromagnetic waves, or electromagnetic waves at a higher energy. Electromagnetic waves are the only one that doesn't require, remember from earlier, does not require a medium, nothing to propagate through. Electromagnetic waves go through empty space. That's why eventually your water will get warm, because the heat from here gets to the inside wall, but only through radiation, not through convection or conduction, because there is no liquid or gas in between the walls of this container, and there's no solid wall like my water bottle. Okay? But radiation can do it. It's why they're not perfect. You can't necessarily insulate from radiation. It's just gonna get there because it goes through empty space. All right. The type of radiation that we're talking about is infrared, that transfers heat. So infrared radiation from the sun, for example, is an electromagnetic wave. Electromagnetic waves, photons, have no heat. They don't have heat built in. They have energy, potential energy. Okay, that's all. They don't have any temperature. They're able to transfer energy through space from the sun to us. The sun is about 8 light minutes from us, okay? Remember, as the photon experiences, it's 0 time, but for us it's 8 minutes from the sun to here. That also means that whatever you're looking at, the sun, let's say, you're seeing what it was doing 8 minutes ago, okay? And that goes for anything that's distant from you. But anyways, importantly, sun releases radiation, and as the molecules in our skin absorb that radiation, our molecules begin to vibrate and shake more. We feel that as heat. Okay, so while you can't see heat with your eyes like you can visible light, you can feel heat. You have sensory perception for heat. You can feel infrared too, or you can sense ultraviolet, the stuff that burns you, because you get burnt and you go home and you go, oh yeah, I got too much ultraviolet today, I'm burnt. Okay, so we have sensory perception for these things, but not direct like we do with our vision. What's important though is that the visible light that we see and the infrared light that we feel are the same thing. It's electromagnetic waves. Okay, but this type infrared has the property that it can speed up your molecules in your skin, and you feel that as heat. You feel warm. Again, it's your skin that is hot, not the radiation. Okay. Let's talk about this last thing for today. Let's put this into context inside an X-ray tube. Okay, radiation, conduction, convection. How do they all play? Okay, well, the X-ray tube, all three methods of heat transfer are used. All right, this disc over here. So this is a diagram of an X-ray tube. This disc here is called the anode. This is where X-rays come from. This opposite side is called the cathode. Okay, the anode is bombarded with billions of electrons. That's how we make X-rays. We run a bunch of electrons into this disk. Okay? When they hit the disk, they slow down. You learned that when an electron changes position or momentum, it emits an electromagnetic wave. Okay? So those electrons are traveling fast. They hit a wall and slow down. X-rays come out of that. Okay? So billions of electrons heat the anode. Okay, and that temperature, that heat needs to dissipate. Okay, so one way that heat dissipates is by this disc heats up this metal rod that the disc spins on, because it's touching the rod. Okay, and inside of this chamber labeled B, there are bearings that allow the rod to spin, to reduce friction and allow the rod to spin. Well, the rod, it's called an anode shank, but anyways, this rod that holds this disc in place is touching those bearings. So the rod heats up because the rod is touching the disc. Disc heats up the rod heats up the bearings heat up what the bearings are mounted to, that heats up the glass of the tube, then heats the oil outside of that, and the heat is conducted outward from the source. In convection, the oil, which is circulated around outside of this glass tube, but inside of the big main cylinder, that mixing oil, hot oil mixing with cold oil, convects or moves heat around in that way. Mixing heated oil with cooler oil, dispersing the heat. A fan blowing on a rubber diaphragm can be used to cool it, blah, blah, blah. But importantly, the oil mixing is convection. Heat is being transferred by a liquid moving in a current. And lastly, radiation. Most heat dispersion from the anode and other metal and glass components takes place by the emission of electromagnetic radiation. This is why you can stand, a couple feet from your oven or a couple, inches from a flame and feel the heat from the flame. That's infrared radiation, like when you feel the heat from the sun. Okay. That electromagnetic radiation in an X-ray tube exits the X-ray tube in different forms. X-rays. In fact, here's an interesting fact. Out of 100% of the energy that goes into an X-ray exposure when you turn this machine on, out of 100% of all the energy created, more than 99.9% of all of that energy turns into waste heat. Visible light, infrared, radio waves, ultraviolet, all of that. Less than 0.1% of all of the energy in that interaction actually turns into usable X-rays. Then we take that less than 0.1% of that interaction and convert that and filter that and collimate that. Okay.
That sounds like a lot of wasted energy.
Well, I was just about to ask, doesn't that sound like a lot of wasted energy, right? So it is a hugely inefficient system, but it's the best system that exists, right? Take a light bulb, right? You ever touch a light bulb after it's been on for a while? It's freaking hot, right? That's all waste energy. Okay, that light bulb heats up the light bulb itself, heats up what the light bulb is attached to, everything that moves from that's conducting energy to heat to all of that. That is all wasted energy. What we want is the visible light. What we're getting is all this wasted energy. So engineers have the tasks of reducing the amount of wasted energy, right? LEDs are a great example of how to reduce wasted energy, right? They last for a long time, so we don't have to replace them. They don't get very hot, right? And they emit light very, very efficiently with very little waste. They're fantastic, right? Light-emitting diode is what they are, and they emit light without all the extra waste nonsense that's required with a regular incandescent or fluorescent bulb like that. All right, there's our talk for today. We made it through a lot. Think how much we learned today, right? So what we're going to do next time is we're going to talk about what an atom is and how they work. Okay, we've got all the groundwork for that now. Alrighty, gang. You guys did great today. Thanks for hanging in there. I know. So